Okay, let's talk about graphing rational functions. So a little review. Remember we defined a rational function as a ratio of polynomials. So we'll have an equation in the numerator, an equation in the denominator. If we do it in such a fashion, then we can actually define the following, right? X-intercepts are when the numerator is 0, right? And those are zeros as well. So I just set the numerator, whatever the equation is, equal to 0 and solve for x. Okay, Y-intercepts are when x is 0, right? That's just a general definition, right? It doesn't have anything to do with rational functions. But it still applies here. So set x equal to 0 and then figure out the y value is. Since we have a denominator, right, it's possible that we'll have vertical asymptotes, and that's when the denominator is 0. So set the denominator q of x equal to 0. And we also have horizontal asymptotes. Again, this isn't specific to rational, but if you want to find a horizontal asymptote, then you just figure out what happens to the y's as x goes to infinity, right? And asking what a y does as x approaches something, that's a limit. So that's why we use limits. All right? Okay, let's go through it. So let's actually graph x plus 3 all over x minus 4. And we're going to do it the exact same way that we approached our previous lesson of finding all the stuff we just talked about. So let's find the zeros or the x-intercepts. That's when the numerator equals 0. So subtract over 3. So x equals 3 is intercept, right? But be careful, x equals 3 is a vertical line. So the actual x-intercept, or 0, is a point. So make it negative 3 comma 0. So now let's do the y-intercepts. Well, this is when x is 0, so do f of 0. And then substitute 0 for all the x's, you'll get negative 3/4. Again, this is y equals, so this is actually a horizontal line. We want a point, so it's 0 comma negative 3/4. All right, so we found the intercepts. Now let's find the asymptotes. So vertical first, do the denominator equals 0, add 4 to both sides, and now this is a vertical line, so we're going to keep that as a vertical asymptote. Find the horizontal. We'll do the limit of this function as x approaches infinity. Remember, I do positive and negative at the same time because then I just do dominating terms, and it all simplifies the same way. And then once I get it simplified, I'll evaluate these two limits. All right, so now I have limit of 1. This means y is always 1. So when x approaches negative infinity, y is 1. When x approaches positive infinity, y is 1. So the limit as I approach negative infinity is 1, positive infinity is 1. This means that the horizontal asymptote is y equals 1. Okay, and again, horizontal asymptote is a horizontal line, so it should be y equals. All right, we figured all that out. So here's our function. Here's our x-intercept, our y-intercept, our vertical asymptote, our horizontal asymptote. And all we need to do is plot these four things and see what we can do with that information once we plot it. So let's pull up a graph. Let's do our intercepts first. So I'll do x-intercept first. It's negative 3, 0. The y-intercept next, 0, negative 3/4. Now I'll do my vertical asymptote at 4. I'll do my horizontal asymptote at 1. And so now it's time to graph. And you see my asymptotes actually break this up into 4 quadrants. And it's a function, so I would never graph in both vertical quadrants. I'd only graph in one. Well, that's tailor-made for. If I know these points are on the graph, it cannot be up here. So it has to approach the horizontal asymptote and then go through these points. And then remember, vertical asymptotes have the behavior of making the function go to infinity, right? Either positive or negative. So I know the graph has to look like this, right? And that's based on the fact that there are points that are in this lower quadrant, right? When I say quadrant, here's the upper piece, the lower piece, and then I know I have to follow these asymptotes. Well, the right side's a little more interesting because it could either be up in this quadrant or this quadrant. For the most part, we just have to figure out which quadrant. So notice that having a point here was very nice because it told me exactly what quadrant I needed to be in. Well, let's find a point. So the vertical asymptote is at 4. So I can plug in any x value to the right of 4, and it'll give me a y value. And when it gives me that y value, it'll tell me which quadrant it's in. So I always choose the one that's just right next to the vertical asymptote. So I'm going to plug in 5. So if we evaluated 5, you'll get 5, and then it'll come out to 8. That means that this function has a point at 5, comma 8. So it has this point. Well, I just figured out that I have to graph in this section, not this section. Right? Again, it's a function, so it can't be in both. It has to be one or the other. So I have to follow the vertical line, cross this point, and then slope or kind of level out to the horizontal line. So it's got to look something like that. All right, so based on all that, I think my graph looks like this. Well, let's use technology. So I did it on Desmos, and this is the actual graph. So good representation. All right, so you want to stop this. You want to complete classwork problem number 1. Okay, so now what we're going to do is let's graph this function, again rational, x plus 1 over x squared minus x minus 2, but something interesting is going to happen, okay? So you'll notice that I can actually factor out the denominator. This factors into x minus 2 times x plus 1, and then you'll see that the x plus 1s will divide out. Okay, so before we do that, notice that it can't be 2, because 2 minus 2 is 0, I would get a 0 in the denominator, right? That's undefined. Well, it also can't be negative 1 because I have the same problem, right? I get a negative 1, my plus 1 is 0. So it can't be 2 or negative 1. Okay, so when I divide these out, which is fine, I just have to let people know, hey, look, even though it looks like I could plug in negative 1, I never could in the original. All right, that's why this comma x cannot be negative 1, because you can't tell from this that x can't be negative 1. All right, so x plus 1 divided by x squared minus x minus 2 is the exact same thing as 1 over x minus 2, where x equals negative 1 is an undefined point. These two are the same, which means when I evaluate all my stuff, I'm going to use this. So why use this complicated one when I can just use this simple one? All right, because they're the same. As long as I never plug in negative 1, they're exactly the same. All right, okay, so let's go through it all again. So if you ever want to graph, you need to find your intercepts. Let's start with the x-intercepts or the zeros. Well, notice the numerator is always 1, so that will never be 0, which means there are no x-intercepts, right, or no zeros. Okay, let's find the y-intercepts. The y-intercepts are when x is 0. So let's plug in 0 for x. I'll get 1 over 0 minus 2, so I'll get a negative 1/2. Again, this is y equals negative 1/2, so that's not a point. So I'll make it an ordered pair as 0, negative 1/2. All right, so now let's find our vertical asymptote. Well, our vertical asymptotes are when the denominator equals 0. So I'll make it x minus 2 equals 0. That happens when x equals 2. This is a vertical line, so x equals 2 is appropriate. And now I want to add another piece. So this is what you need to make a note of. I got to take into account this x equals negative 1. So x equals negative 1 is an undefined point. It doesn't exist. It isn't a vertical asymptote, or else it would be here in this equation. It's just a point that doesn't exist. All right, so now let's figure out what that y value is so that I can put a nice open circle on my graph. So let's evaluate the function at negative 1, and again, this function. Okay. And I'll show you at the very end, something interesting happens if we evaluate this function at negative 1, but we're going to go with our simplified version. So it's 1 over negative 1 minus 1, so this is negative 1/3. So there's an undefined point at negative 1, negative 1/3. Okay, so vertical asymptotes come from the 0 to the denominator, and simplified versions, when it simplifies out, then this is an undefined point. Now let's do our horizontal asymptote. Same thing. Let's find our limit as x approaches plus or minus infinity of this simplified version. I don't need to worry about that it can equal negative 1 because I'm going to infinities. Negative 1 isn't anywhere near positive negative infinity. Well, this is all simplified, so all I have to do is separate into two limits and plug in negative infinity. So if I plug in negative infinity, I get 1 over, this all simplifies to negative infinity, so 1 over infinity is 0, right? So think about 1 over the largest number ever will be the smallest number ever, which is 0. Now do 1 over positive infinity, so again 0. So my horizontal asymptote has to be y equals 0. All right, so let's do our stuff again. So I have the x-intercept, which is none. I don't have any x-intercepts. I have a y-intercept at 0, negative 1/2. I have a vertical asymptote at x equals 2. I have an undefined point at negative 1, negative 1/3. And I have a horizontal asymptote at 0. So at the least, I can put all that stuff on a coordinate system. So throw it up. There are no x-intercepts, so I won't apply anything on the x-axis. Here's my y-intercept. Here's my vertical asymptote at 2. Here's my undefined point at negative 1, negative 3. And I'm going to make it just an open circle, right? That's how we graph undefined points. And then here's my horizontal asymptote right on the x-axis. And you can see on the x-axis is probably why I don't have an x-intercept. Remember, though, that doesn't mean you can cross horizontal asymptotes, but our equations aren't going to do that. But there are equations that do, but ours won't. So same rules apply. I can't graph in both. I have points in the lower section, so it must go through these points. So I'm going to have a graph that looks like that. And same thing, I don't know if it's in the top section or the bottom, so I'm going to just plug in a point. And now my vertical asymptote's at 2, so I'm going to do the next one, which is 3. So I'll do f of 3, that equals 1, so there's a point at 3, 1. So plot 3, 1, and you'll see I figured out what section I should be graphed in. So I'll follow the lines, go through the point, follow the line. So that's what I think my graph looks like. Well, let's check it. So that's what I think it looks like. Here, if I graph, again, I'm graphing x plus 1, x squared minus x minus 2. I'm going to graph that in Desmos, and this is exactly what I get. Okay, you need to be careful, though. I put in this undefined point, right? Technology will not show you these. All right, not when they graph them. It's a single point. It's a pixel, right? You can't see a missing pixel, right? So you have to know it's there. That's the part about you got to be a little smarter than the technology, right? The technology knows it's there, but it just visually it can't show you it, all right? But if you were to plug in f of -1, the technology would tell you error, all right? But it won't show you on a graph, so you have to know it's there, okay? All right, so here's the deal. A vertical asymptote sometimes is not a vertical asymptote because it gets simplified to an undefined point. So when the 0 in the denominator, and remember zeros in the denominator produce vertical asymptotes, when those simplify out, it's actually an undefined point, not a vertical asymptote, okay? And a really nice thing here is if you ever go into your original function, you plug in that value and you get a 0 over 0, this 0 divided by 0 is a huge telltale sign that there's going to be something that divides out, and it's going to be one of the denominators. All right? So there's something in the numerator and there's something in the denominator that both create a 0, which means those factors have to be the same because this is the x equals a, which will produce those zeros. All right, so let me show you how this works. So here's the one that we did before, right? And we know that if we factor it all out, the x plus 1s divide out. Well, what happens if I were to plug in this -1 to this function? I'll get, all right, a -1, which is -1 plus 1, which is 0. And -1 squared plus 1 minus 2 is 0. I will get a 0 over 0. And this 0 over 0 would tell me that somehow in this denominator, numerator, and denominator, there are two factors that match up. That's how I get a 0, right? That's how I get a 0 in the numerator and a 0 in the denominator when I plug in x minus 1. And in fact, it lets me know that it's x plus 1 that's the factor because I'm plugging in -1. All right, so make a note. This 0 over 0, when you're doing rational functions, is a big telltale sign that something will be able to divide out. All right? Okay, so that's pretty much the end of the video. So you want to stop this complete classwork problem number 5.